All right, so today we're going to continue with a little ionic bonding. Again, we're picking right up with your PowerPoint again, starting on slide 23. That way you can sort of kind of be filling out your notes and following your notes as we go. Big thing here to remember, and I know I keep ramming this down your throat, but it's huge. Everything here is about stability. We want that noble gas configuration, which means everybody wants those 8 valence electrons, everybody in the S and the P blocks, except for hydrogen and helium, who want 2. Now, transition metals, like we said yesterday, they can't really get to be that noble gas. So they really aim just to fill up an orbital or half full orbital for some measure of stability. But again, it's all about stability. So yesterday we talked about how they can form ions in order to get that stability. Today what we're going to talk about is how they can actually join together. Okay, where do these electrons go to make them stable? So anions and cations can join together to form something called an ionic compound. Okay, ionic compound is also called salt. Now, I know what you're thinking. Oh, hey, I use that stuff on my French fries. Well, yes, but believe it or not, sodium chloride is not the only salt. Any ionic compound is actually called salt or a salt. And the way it's formed, this is a key thing for you guys to know, is by the transfer of electrons. Okay, electrons are being transferred from one to the other. Best example ever is the one you're most familiar with, sodium and chlorine. Okay, chlorine has 7 valence electrons. Sodium has 1. So what's happening when we put these two guys together is this electron is actually jumping over here. Okay, when that electron moves over, my sodium is left with a positive charge and my chlorine gets a negative charge. So by virtue of that electron moving, these two are now connected together by electrostatic forces. It's just like magnets. When that electron moves, it's like you get a south end and a north end that are now clinging together. Okay? So, ionic compounds made by transfer of electrons. And there's always going to be, they're made of a positive and a negative ion. Okay, you could also say a cation and an anion. And then because of the way the pattern is on the periodic table, you can say these are made of a metal and a nonmetal. Okay, you need to know that. So remember, ionic compounds are made of metal and nonmetal, positive, negative, cation, anion. It's all the same thing. Those polyatomic ions that we learned about before can also be part of this, but they are cations or anions, positives or negatives, so they are definitely a big part of this. The other thing I want to mention before we get into how this happens is the simplest ratio of elements for an ionic compound is called a formula unit. Okay, the formula unit is basically what is the smallest possibility. So if you have a salt shaker, okay, you got a whole bunch of grains of salt in there. You take 1 grain of salt, it's a whole bunch of sodium chloride bound together. When you break it down, the formula unit is your sodium ion and your chlorine ion joined together. That's really what it is. The other thing that's mentioned in your notes that's worth you taking a peek at is what kind of properties do we have with ionic compounds. Okay, you get that regular repeating arrangement, and there's a great picture in there that I won't even try to draw here. But the big thing to remember is that your structure is fairly rigid. Okay, you've got a really strong bond when you transfer that electron, a really strong bond. Think Legos. Okay, they're put together and they stay together. Can you take them apart? Absolutely. But they are still very, very strongly bonded. That strong bond gives them pretty high melting points. Because if you think about it, to melt something, I've got to take those hands that are clasped together and allow them to roll around each other, if you remember what I was doing in class. So if they're really tightly bound, that takes more work. That's a higher melting point. They're also good conductors. Okay, ionic compounds are very good conductors of electricity when we dissolve them in water. So, let's talk about how this process works. I'm actually going to show you 2 different methods for doing this. Believe it or not, I want you to try them both so that you can decide which method you like better. All right? So, what we have here is we have a calcium. This is great animation in your PowerPoint. It'll probably look better than this video. And we have a phosphorus. 2, 3, 4, 5. Okay? If these guys are going to bind together, what I have to remember is I want everybody to be stable, and I need all of my electrons accounted for. So the first thing I'm going to do is I'm going to move these electrons over from calcium. Okay, so to keep this from getting too messy, just kind of follow along with me here. I'm going to move these electrons over here from calcium. Okay, and I'm going to take my little eraser and erase all this. So now I have a stable calcium. Woohoo, awesomeness, he's good to go. Okay, but now I have a problem. Is that phosphorus stable? No. Okay, he's not stable. There's only 7 electrons. So when you think about what I can do next, I can't just randomly pull an electron and go, all right, I'm going to add another dot right there. You can't do that. Electrons don't just come from anywhere. Okay, you can't say, well, I'll just add a sodium. Sodium's got 1, so that'll work. Well, that makes a whole nother compound. We just want calcium and phosphorus getting together here. So believe it or not, the only option we have is to add another calcium. Okay, so here's my calcium. He's got 2 valence. I'm going to take one of these guys, I'm going to move him over, stick him on my phosphorus. Now my phosphorus is nice and stable and happy. Okay, he's got his negative charge. Woo! But there's another problem. The problem is, now my calcium isn't stable. Daggone it. So what am I going to have to do? I'm going to have to add, oops, let me make these green. I'm going to have to add yet another phosphorus. 1, 2, 3, 4, 5. Okay, so I can move that electron over from calcium, all right, making him another happy camper. You can already see where this is going. Problem now, yep, calcium is good, but that phosphorus is not. So I'm going to introduce a third calcium, okay, and as I move the electrons from this third calcium over here, when I take a look at it now, okay, well, this guy's happy, he's good to go. And then let me erase the ones I moved. Oh, he's happy. He's good to go. Now everybody has got a full outer shell. This is how we do ionic bonding with these dot diagrams. It is very visual. You need an eraser to do it, but you won't mess it up if you just very slowly and carefully move your electrons. The formula is the last thing we have to come up with. Okay, what's the formula when we put calcium and phosphorus together? Well, I just count the calciums, there's 3 of them, and I count the phosphoruses, there's 2. So the bond between calcium and phosphorus makes Ca3P2. Okay, Ca3P2. Now, they're not all this complicated. If you look in your notes, there is another example that has sodium and nitrogen. Okay, this one is much more straightforward. Sodium has 1, nitrogen has 5. Okay, so we move 1 from sodium. All right, nitrogen, not happy. But usually people can fairly quickly see if I add a second sodium and then a third sodium, then these is gone, these are gone, and I end up with Na3N. So they're not always as complicated as that first one, but by doing dot diagrams, you can visually see what's happening. We're trying to transfer electrons to make everybody happy. Okay, that's the first method I'm going to teach you. The second method for making ionic compounds is you have to realize that by writing a formula, the compounds are neutral. Okay, compounds don't have a charge. The ion has a charge, but when I put this thing together, I want that entire compound to be neutral. So I've got to add the right number of subscripts to represent the number of atoms I need. So the second method is called the crisscross method. What I'm going to do is I'm going to write both of my ions down. Okay, I got iron, which is a +3, that's the one I'm giving you, and sulfur, that's a -2. That's step 1. Step 2, I'm going to draw arrows that cross each other. Okay, this is called the crisscross method. That's why. Step 3, I'm going to take the charge and put it at the end of that particular arrow. So iron 3, I'm going to take that 3 and put him right there. Sulfur is a -2. I'm going to take that 2 and I'm going to put him right there. Believe it or not, you have just found the formula. Okay, your formula is Fe2S3. Okay, a lot of people love this crisscross method. And what you'll realize by doing it is +3 times 2 is a +6, -2 times 3 is a -6, and the entire thing ends up being neutral. The only thing you've got to be careful of with your crisscross method is you might have to reduce. For example, if you have Fe2 and oxygen, okay, according to my crisscross method, I carry that 2 down there, carry that 2 down there, okay, here's my formula. My formula is Fe2O2. But the reality is that's actually wrong. Okay, you really don't need 2 irons to bind with 2 oxygens for a formula unit. Remember, the formula unit is the most basic simplified version. It's really FeO. So when you use the crisscross method, just be aware that there are times you may have to reduce. The other thing to remember about the crisscross method, or about any method, is using polyatomics. Okay, polyatomic ions, the biggest thing I can tell you is you cannot change them. Phosphate is PO4. No matter what, you don't get to change that. Just like the symbol for copper is Cu. You can't look at that and say, I don't like it, I'm going to make that CO. Like, you don't have that option. Ditto with your polyatomics. So when you do compounds with your polyatomics, your rules stay the same. So sometimes it's easy. Okay, sodium and hydroxide. Sodium's a 1, hydroxide's a 1. Well, that's easy. It's Na1OH1. Okay, that's a piece of cake. But other times, it gets a little harder. Let's say I have magnesium, which is a 2, and hydroxide, which is a 1. When I do my crisscross, 2 and 1, circle, circle, I get 1 Mg and 2 OHs. But I can't write it like this, because this means 1 Mg, 1 O, and 2 H's, and that's not right. So what you have to make sure you do is put that polyatomic in brackets, okay? And you have to consider that if it has its own subscript, okay? Look at copper 2 and phosphate, okay? Copper is a 2, phosphate has a charge of 3. So when I look at the formula for this, it's copper with a subscript of 3 coppers, and I need 2 phosphates. Okay, phosphate is PO4, and I need 2 of them. I don't get to make it PO8. I don't get to make it PO2. You don't get to change the formula. You have to leave it as is. This ionic bonding takes a lot of practice. So don't just sit here and go, okay, I got it. Do your practice problems, get them checked, get extra help if you need it, and you will rock this stuff.